Potential energy diagrams. These are going to be our link between kinetics and thermodynamics. So recall, we've talked about the fact that chemical bonds are stored energy, aka potential energy. Because of this, we use potential energy diagrams to illustrate the potential energy or stored energy changes that occur during a specific chemical reaction. So when we defined a reaction, we said it is the breaking and reforming of bonds. So we break our reactants to form our products. The heat of the reaction, then, is the amount of heat energy lost or gained throughout the reaction. So think of the H and delta H to represent heat. So we have enthalpy. So the potential energy of the products minus the potential energy of the reactants. So delta H is products minus reactants. So the potential energy is the stored energy of the reactants and the products. So we're talking about how much energy is being stored in the products versus what we started with. So a change, when we're calculating a change, it's our final minus our initial. So our products minus our reactants. So recall there are two types of reactions. Reactions that release energy are exothermic. So we have a negative delta H. And energy is released, it's going to be on the right side of our reaction because it's coming out of our reaction at the very end. It is a product. So an example, when we put sodium in water, we have lots of heat, even fire produced as a product. The heat can be felt if you touch the outside of the container. That heat is leaving the reaction, is leaving and is being produced and leaving the reaction. Or opposite, we have endothermic. Reactions that gain or absorb energy have a positive H, and we call it endothermic because energy must be added to the reaction. So it's positive because we add it in as a reactant. It gets added into the total reaction. So endothermic, added in, into, endo. So an example would be baking. We have to have an oven to supply the heat. There's a lot of possible examples here, and maybe write a few more for yourself. You are used to looking at a reaction as a forward reaction. So it's a reaction that reads from the left to the right. So forward, going from the left to the right. A reverse reaction would be when the reaction goes in the reverse direction. Reverse reaction goes from the right to the left. And you can read our potential energy diagrams as a forward reaction. So we go on the forward way, or as a reverse reaction. Start down here and go the opposite. Now my activation energy is the energy required to activate the reaction or to get it started. The energy needed to get it started. So if we're trying to make this reaction occur, we have to add a certain amount of energy in order for the reaction to occur at all. If I do not have enough energy, enough added energy to reach this point, I won't keep going over. If I have enough energy to reach right here, it still won't occur. I have to have enough energy to reach all the way to the required activation energy amount. This would be the amount of energy required to break the bonds to activate and start the reaction. Once I have this much energy, the reaction can occur. So it's kind of like pushing a rock up a hill. If you don't add enough energy to get it all the way to the very top of the hill, the reaction can't occur. The ball will not roll down the hill. If you stop even just right here, it'll fall back down. There will not be enough energy to complete the total process. So you must get over the hump in order for a reaction to occur. So if we look at a potential energy diagram, we have our reactants, our products, our change in energy. So as I go up my activation energy and go down to my products. My activation energy is the amount of energy I started with to the amount of energy that needed to be added. So this part right here is activation energy. Now my overall energy which is what I call my delta H, this is only the difference between my reactants and my products, which means this activation energy does not affect my delta H, which becomes important when we're discussing a catalyst. So we said that a catalyst shortens the reaction time. It speeds up the reaction. How does it do it? Well, the activated complex is lowered, or the amount of activation energy is decreased, or we say the reaction pathway is shortened. What I mean by all of these, my activated complex is right here. We're going to talk more about what that is, but it's what is produced when enough energy occurs to begin breaking all the bonds. So we have our activated complex here. This is at a lower amount of energy whenever we've added a catalyst. So at this line, this is my catalyst or my enzyme. So my activated complex is lowered, or we say my activation energy is decreased. This was my original amount. Now it's been lowered all the way to here. And my reaction pathway is shortened, meaning the distance between where I start on my reactants and end on my products, this distance is much shorter. Which the speed of my reaction is how often this occurs. If all three of these things have been lowered, this will occur much more often. These reactants will collide to form my activated complex more often because I have a lower amount of activation energy. So more of my collisions will be effective. They'll be colliding with lower amount of energies, but the activated complex will still be produced because we have a lower amount of necessary activation energy. So let's look at the two different types of potential energy diagrams, whether we're talking about it being endothermic or exothermic. So when it's endothermic, it has a positive delta H. My product side to the reactants in comparison is always higher. My products will always be higher than my reactant side, meaning that energy is absorbed. So let's go through and label an endothermic potential energy diagram with each of the following. First, we'll label the potential energy of the reactants. Well, my reactants are here, so we'll put an A. This side, my y-axis, is showing how much potential energy there is, so where my reactants are is their potential energy. B, potential energy of the products. C, potential energy of the activated complex. Well, your activated complex is at the peak of your activation energy hill, so that's right here, my C for my activated complex energy. D, the activation energy of the forward reaction. So from where you started, how much energy was added? So I started down at this line, and I went all the way up to this line. So the difference here is my activation energy of my forward reaction, so D. My activation energy of the reverse reaction. Reverse meaning I start here and go here. Well, my activation energy here is I start here and go to there. It's very different at this point. I'm going to here, and I start right here. So this is my E, the activation energy of the reverse reaction. And then the total heat of the reaction, or my delta H, would be my products minus my reactants. So my products are here, reactants energy is here, so delta H is always the difference between my products and my reactants, and notice how it's positive this time. So we label this F. Now to define the activated complex, the thing that sits at the very top of the activation energy. The activated complex is the highest energy point of the reaction. This is where we have a full rearrangement of the reactants. We have enough energy, we have enough activation energy to reach this peak, and at this peak we have now broken all the bonds holding everything together, and we have a full rearrangement occurring. Remember, this must happen for the reaction to be successful. We must break all of our starting bonds to form all of our new bonds. Now for an exothermic potential energy diagram. So for exothermic, now we have a negative delta H. So we have our product side to the reactant side will always be lower. So our products must end up being lower than our reactant side because we have a negative change in energy. So we have energy being released. Now remember, I said a negative change in energy. We are not releasing negative energy, just a overall negative change from what we started with to what we end with within this reaction. So we'll once again label this potential energy diagram. First, we'll start with the potential energy of the reactants, A, potential energy of the products, B, potential energy of the activated complex sits at the highest most point, C. Next we have the activation energy of the forward reaction. So we started our reactants, move up to the activated complex. So this change here is our activation energy of our forward reaction. We label that D. Activation energy of the reverse reaction. This time we're starting out at the products and we're moving up to the activated complex. So if we use this line here, this would be our activation energy of the reverse reaction, E. A much larger hill here means much more activation energy. And my delta H, my change in heat of the total reaction, would be, we label F. It is our difference between our products and our reactants, and that would be a negative delta H. So I have a couple questions here that I want you to try and answer on your own first, and then I'll go through the answers. So for the first question, if a catalyst were added to the above diagram, which letter quantities would change within the diagram? So a catalyst lowers my activation energy, it lowers the activated complex, and it shortens the reaction pathway. So let's draw in what this catalyst would look like for here. That'll help with this answer. My catalyst would shorten and lower this bump here. So what letters would that change? Well, that doesn't change A, it doesn't change B, and it doesn't change F. What it does change is the location of the activated complex C, the activation energy of the forward, and the activation energy of the reverse reactions. So C, D, and E. So would it change the delta H of the reaction? No. It remains the same. And finally, what are the benefits of adding a catalyst? Well, by adding the catalyst, we lower the activated complex, lower the activation energy, and reduce the reaction pathway. Which overall speeds up the reaction, RXN, reaction. Now use these notes to complete through page 7 of this packet.